Good afternoon from Europe, and this European standard EN 16798 Part 1. This is under revision, and design for airborne transmission is included in this ongoing revision process. So just to say that, as Bill already told, this applies for long-range transmission, which can be affected by ventilation design as well as air cleaning. So we speak about these removal mechanisms, which we have natural ones, and that can be achieved with general ventilation design, basically. This revision is ongoing so that the standard provides an opportunity for infection risk-based ventilation design. This is a kind of opportunity to be specified by the client when this method can be used, so it is not a mandatory. Method is based on Wells-Riley model, and this is a quanta method, and as we know that quanta values may have very high variations. So median viral load values have been provided as a default values in the informative annex, but when the standard is built so that in national annexes it is possible to specify national values and to select the relevant levels for this viral load. And there is quite a dedicated infection risk control concept is applied based on the basic reproduction number, which is defined during a pre-symptomatic period and will account all possible out-of-home interactions with suspectable persons. So basically this means that the method is limited for non-residential buildings. So residential buildings where people are at home are excluded from this standard, and also this standard is not dealing with healthcare setting, which will need much more strict risk levels to be established. When these ventilation rates, target ventilation rates, are first provided for fully mixing air distribution, but there is also ventilation effectiveness specified as a point source ventilation effectiveness to recalculate for actual air distribution solutions. So this will be the complementary for existing perceived air quality ventilation, which equations I hope you all know very well, depending on the number of person and then number of square meters, so floor area. This will stay as it is in the standard, and when this infection risk-based design ventilation rate calculated should be compared with this one, and then it would be logical to select the highest one of these two. So originally this method, what is now proposed for the standard, was proposed by Nordic Ventilation Group and REHVA, but in the standard it is developed a bit so to be more generic. So you can see this very simple generic equation which allows to calculate infection risk-based target ventilation rate, so that there are only two parameters in the equation, which are the number of occupants, so this N, and then the room volume. And there are two factors which are quantum emissions specific ventilation rate, that is a constant, and another constant removal rate of viruses, including decay deposition, and can include also air cleaning. So basically, to apply this equation, a standard provides tabulated values for these two parameters, and then only the number of occupants and the room volume are the parameters needed by the user. So this equation is originally based on quanta, but as in this generic form, it may also be used for the relative risk reduction, it is possible to recalculate these parameters also in that purpose. And it allows also so-called reverse engineering. So it means that if one knows already given ventilation rate, so from this ventilation rate and room volume, it is possible to calculate how many occupants can safely to be in such a room. And these tabulated values are provided for main non-residential room categories, as you can see, for classrooms, offices, assembly halls, meeting rooms, restaurants, and gyms. And it is so that depending on the activities, it is known that these quantum emission rates will be higher if we have active speaking or active physically active when the values are higher. And the second parameter is QR, it is 0.24 if we speak only deposition and decay. But if there is an air cleaner applied, then this KF, so this filtration removal rate, can also be included and taken into account. Compared to the logic of a perceived air quality-based ventilation, which introduced 3 or 4 categories, in this case there is no categories. So it's basically following the risk concept, and only one value can be then calculated. So these tabulated values are provided in the informative annex, and it is a possibility according to the logic of this standard to provide so-called Annex A values, which are national annex values, and to provide then different values. But yes, the generic equation is a starting point for this infection risk-based ventilation calculation. So then we also stress the importance of ventilation effectiveness, and in such an infection risk scenario where we are basically expecting that one infector could be in the room, so this will correspond to point source. And in the existing literature, typically ventilation effectiveness values are available for distributed source, which corresponds to normal occupancy, so all occupants in the room emitting CO2 and pollutants, but infection risk situation is different. There is only one occupant emitting, and this is called as a point source ventilation effectiveness, what then needs to be calculated. And for that purpose, a calculation method is provided. So this point source ventilation effectiveness can be measured with a tracer gas measurements. At least 2 source locations would be needed for that purpose, or it is also possible to use CFD simulations for this purpose. I just show one example. This is quite a large classroom where you can see that there are many supply air devices and also extract air terminals. And in the locations close to the source, local air quality index is low, and this indicates that the concentration, tracer gas concentration, is high. And when the tracer gas is distributed in the room, so that on the right side, where the source is located in the middle of the room, for some reason higher concentrations are at one end of the room and much lower concentrations at another end of the room. So this illustrates the need to conduct these tracer gas measurements with different point source locations, and then these average values can be calculated from the local air quality index. And in this case, this point source ventilation effectiveness has resulted to 0.76 and 0.77, so the average value in this case 0.76, where in fully mixing this should be equal to 1, showing that we need more ventilation because the ventilation effectiveness is less than 1. This is one example of an application in the typical classrooms. If we just take a small classroom row, what is the first one here, we can see that ventilation rate calculated with infection risk-based equation is about 7 liters per person. Next classroom provides 9 liters per second. And these values are then compared with category 1 and category 2 values in the existing standards, so which are perceived air quality ventilation equation based. And in the case of these highlighted cases, actually these perceived air quality ventilation rate is higher. So it shows that in common classrooms, also in offices, it's quite typical that infection risk-based ventilation does not need to be very high value, but rather we can expect that category 1 ventilation rate will be higher. But when we will go on in this table, then actually these meeting rooms can already provide very, very large values, which then actually show that it is reasonable to reduce the occupancy in the epidemic situation, and then more realistic ventilation rates can be achieved. But as a phenomena, it describes it very well. Meeting room heavily occupied, high infection risk, so it is a good reason to reduce the occupancy and perhaps also to increase the ventilation rate in the epidemic situation. In the standard, it is also addressed now operation for the optimal indoor air quality. So it means there are recommendations how to do it in the epidemic periods and how outside epidemic periods demand-controlled operations can be used. This is something what has not been addressed in the previous version of the standard, so this operation for optimal indoor air quality is a very important addition. So basically, to conclude, revision is proposing normative but selected by the client design method for the airborne transmission, what is not mandatory to apply, but this opportunity is provided. Method also allows reverse engineering. One can calculate the max occupancy for epidemic periods at the given ventilation rate, and the importance of the ventilation effectiveness is stressed. So, and these airflow rates are quite realistic for typical classroom and offices, and in other rooms, yes, reduction of occupancy can be also a reasonable measure together with advanced air distribution solutions.